All right, so we'll go ahead and get started now. So I'm Sid, and I'm joined here by my partner for programming last season, Niket.
Hi, I'm Ket.
And also I'm joined by our team captain, Pranay.
Hi, I worked on the hardware for Team Juice last year. So when we get to the odometry part of this presentation, then I'll be explaining the hardware that's involved in specifically dead wheel odometry.
Yeah, so this workshop is going to be about, we're going to be giving an introduction to PID, how to implement it, and like what the advantages are, and all the math behind it. And then we'll wrap it up with, like Pranay said, an overview of the odometry modules and like tips and tricks on how to implement that too. All right, so first of all, I'll be going over kind of what PID is. So PID is, like it says here, a feedback loop mechanism, meaning that for if you're trying to get to a target, it'll give you some sort of correction type value, which is based upon your how far you've already moved. So feedback means that it's taking into consideration the actions of your robot previously to determine what the new correction values and power applied to your robot's wheels should be. And PID isn't just in robotics, it's an industry standard system. It's used in a variety of things that wouldn't necessarily need error correct, or you wouldn't think would need error correction. But like, for example, in a coffee machine, when you're brewing coffee, you have to brew it at a certain temperature, right? So what PID allows the coffee machine to do would be to make sure it gets to the temperature that you want it to be at, and that it maintains that temperature for when you brew it. And it's also used in cars for like cruise control. If you're trying to go like 70 miles per hour, it'll right now you're going 60 miles per hour. It'll speed you up and then keep you at 70 miles per hour. So that's the purpose of PID. It uses your previous actions to determine what values need to be changed in the future to get to your target. Now, why would you use PID versus something simple like run to encoder, which is already built into the FEC library? So PID allows you to have an increase in speed for motions. Run to encoder, if you try and do it quickly, you can overshoot your target. So most of the time you have to use run to encoder slowly. And so what PID would allow you to do is in the first section of your motion, you can move very quickly. And then as you get closer to your target, you can slow down so that you'll be able to actually reach your target without wasting time by going very slowly. And then another benefit is that it can actually fix collisions. If you noticed in the Skystone autonomous period, there's a lot of possible collisions. You can run into the stones that have been tossed around, or the bridge, or your alliance partner. And what PID allows you to do is it can actually fix like a rotation issue or a position issue if you run into something. And although this isn't 100% accurate, it's still far better than anything that run to encoder or similar systems could do. So now we'll be talking about how does PID work. So it, like I said before, it takes the input of where you are right now, and then it returns a correction value, which is then applied to your motors, so that you can efficiently reach your target without overshooting it. So every loop of your robot's autonomous, which are normally called ticks, you send in your input value of where you are right now, and then it'll do some mathematical calculations, which I'll be going over, to return the correct correction value that then you apply to the robot's wheels. And PID is a calculus-based system, but I'll be making sure to go over everything that you would need to know if you didn't already know calculus. And what PID stands for is proportional integral derivative, and I'll be going over each term in depth so that you can see how it works and how to tune it. So yeah, the next section of this will be the math behind PID. So this complicated looking equation is the full equation of PID in its mathematical terminology. So I don't want you guys to get like scared by this equation if you don't know calculus, but basically I just want to define a couple things. So this variable E of t means the error at that time t. U of t is the correction at time t. And then this Kp, Ki, and Kd are all just constants, which are applied to each part of the PID equation. So then I'll be starting off with the proportional term. So what this means is simply that the proportional portion of the error is proportional to the error at that time. So Kp is just a constant, could be anything like 0.5, 0.1, whatever, that you multiply by the error. So if your error is 10, where error is the target minus where you are right now. So if you're at 0 and your target is 10, your error is 10, right? If your proportional constant is 0.1, then your correction would be 1. And so it's the most simple portion of the PID loop. And now I have some graphs down here of what can happen if your proportional constant is too high or too low. So if it's too high, which is this right graph, your robot will go very quickly and then most likely overshoot the set point being your target value. And then it'll then come down and it'll oscillate rapidly around your target value, which causes inaccuracies because, as you probably have experienced, your robot doesn't drive exactly forward. It'll rotate a bit or strafe a bit. And so this causes a great deal of error. And then this is what could happen if your proportional value is a bit too low. Your robot will go up kind of slower than it should be, and then oscillate slowly around the target. Now, what we found is the best for robotics is to actually tune your proportional value so you never reach the target with just a proportional correction. If you've like experimented with the power applied to motors in your FDC robots, you might notice that if you go to around 0.1 power, it varies per robot, but something around that, you won't actually be able to move your robot. Because the weight of the robot is too much for that little power to actually move the robot. So what happens is, as the proportional value gets too low, your robot will just stop moving because it doesn't have enough power anymore to actually move forward. So we found that the best tune is to, if you can see my pointer here, is that you go, you start off kind of a medium amount of speed, and then it kind of approaches the target without ever actually reaching it. So I'll address how you finally reach your target later, but if you do this tune, then it should be that the error gets your robot pretty close to your target without overshooting it.
And when Sid says target here, he does mean target distance.
Yeah, sorry, that's what I meant. So then I'll be going over the integral term. Basically what an integral is, for everyone not in calculus, is it's the area underneath a curve. So the error the curve that's talking about here is the error versus time curve. Now, these graphs down here aren't error versus time curves. An error versus time curve would look something more like this, because your error reduces as you get closer to your set point. And so what the integral term does is it builds up as you continue your motion. So at the start of your motion, the largest contributing factor will be the proportional portion of PID. And so as you get closer to your target, the integral portion will have built up because it's the area underneath the error versus time function, right? So it'll build up as you continue your motion, and then that'll push you over the edge to actually reach your target. If you can see on the right, this is what I was talking about a proper proportional curve, is that it goes up and then plateaus, right? It doesn't have enough power to move further. a proper integral motion or an integral tune then would be that you move forward and then around at this area we're starting to flatten out. The integral portion is built up enough that it kicks in and pushes you to the target value or just a bit above. And so I think that's the best tune for the integral portion. And what you can see is if your integral is too high, it'll be built up far before you ever plateau. And so you'll just kind of rocket up and overshoot your target value, and then you'll come down. But that overshoot can be kind of dangerous because let's say for this season, if you're trying to move to the skystones, but then you overshoot and just ram into the skystones, you probably won't be able to pick them up. So yeah, that's how you should tune the integral portion. And another thing that I want to mention is something called integral windup, which is basically if you actually reach your target with a proper integral tune, the integral portion of the PID correction will be built up quite a bit, so you'll just overshoot the target once you actually reach it. So we'll address how to solve this issue later once we actually get into the programming of it. And and so yeah, that's the proper tune for the integral portion. Next, we'll be going over the derivative term. Now, all a derivative is it's the slope at a certain point of the error versus, or at a point of a curve. So in this situation, it's the slope of the error versus time curve. So normally what you'll see is if you just have P and I, your motion will be rapid and it will be your speed will be adjusting rapidly. And what this can cause is if you quickly go down in speed or quickly increase your speed, your robot can, it'll kind of screw up the motion because it might turn a bit or it'll strafe a bit because the power applied is just very drastic. So you'll have a lot of slippage. So normally what you do is you can subtract the derivative portion, meaning you subtract the slope. As you can see in the graph down below, when you're moving up quickly, or when your speed is increasing quickly, the derivative or the slope is very large. Meaning if you subtract the slope, the power will be smaller. And the same goes the other way for negative, when your slope is negative, when your power is decreasing rapidly. And the main point of this is just to smooth out your motion so that you have less error in the motion.
Really quickly, while the derivative term is really useful for certain applications, we don't actually recommend using it for FTC because it'll introduce a lot of problems. And so you can just set the KD constant to 0 and it'll be a lot simpler generally.
Yeah, because the thing is when you tune just the proportional and integral portion, it's far easier than managing 3 different variables, because if you increase KD, you might then start not reaching your target. If you decrease KD, you might overshoot, and then it's too many variables to take into consideration, and it'll like exponentially increase your tuning time. So we found that's not necessarily worth it to introduce the derivative term, but you can if you have the time or if you feel the need to introduce it. All right, now I'll hand it off to Niket to go over the programming of the PID loop. So I'll stop my screen share and then Niket can take over.
Yep. Okay, so we're gonna start off with this simple empty class here. And this will be a sort of object-oriented way of going about implementing PID into your FTC code. So we're gonna start off with the PID controller class. So let's start off with a constructor. I'll explain what all these variables we'll do in a sec. So the P, Ki, and Kd are your 3 variables that you're going to be using to tune your PID controller. And we're going to make these all global variables so we can access them in any part of the code. So I'll do that right now. And the set point here is the same as the target value or target distance.
Yeah, set point, like as you saw in the graphs, is just interchangeable with target.
And the reason we don't say target distance is because PID can not only just be used for lateral or horizontal movement, it can also be used for rotation and really a variety of other things. And you'll be able to use the same PID controller class for all those purposes. So right here, we're just going to set those global variables.
And global variables just mean it can be accessed anywhere in the class.
All right, so now I'm going to define some other variables, and these might be confusing at first, but I'll explain what they do later on in the code. So this system, the current time millis function, just will figure out it's just the function that'll return the current time, really.
Error sum is the you'll see becomes the integral portion of the PID loop.
And then we're going to need to make last time a long instead of a double because of the Java data types. I believe that's it that's it for the constructor. So now we're going to make the function that'll return your correction value. And this is the one that we run every time our autonomous program will loop. So essentially it's constantly being run. And the new input would be the current the current distance that we've traveled, and you can measure that with odometry, like we'll talk about later, or with just reading the drivetrain motor values. And we'll show an implementation of this in a second. So first thing we're going to do is define some new variables, and this will store the current time. Because as this function, as your time progresses, we want to be able to store both the last time and the current time, and then we can calculate the distance between those, which would be our period. So copy this. Then we're also defining a function for error, a variable for the error.
Yeah, so this next portion, I'll be kind of explaining what each mathematical function does when the cat types it out.
Yeah, all right. So first we have the error, and then this is really simple. It's just going to be our target value minus our current value. Yeah. So this next function is to address the integral windup issue Sid mentioned before, which was essentially where even after it reached our target value, the integral will still have a decent amount of will still be quite high and won't be 0.
Yeah, so when you overshoot your target, the integral portion will slowly start to decrease, but if you actually don't implement this portion, you'll see that it takes a long time for the integral portion to decrease back down to 0. So the best way to solve this is we found that every time that you reach your target, which would be when your error is 0, you should just set the integral portion to 0. Now, how we do this is we just see if the last error's sign is different than the current error's sign, meaning negative and positive or positive and negative, then that means it's crossed 0. So because of that, we can see when it crosses 0 and then set the error to 0.
Yeah, and then
Or sorry, we set the integral to 0.
Yeah, and then math.signum is essentially just a function that'll return the sign of any object, of any integer. So for example, if this is negative, then this will just return -1. So we're just checking if it crosses the line essentially.
Yeah, and now we'll be addressing the integral, how to actually calculate the integral portion, which Niket will type out.
Yeah.
So you can't actually integrate the error versus time function, really. So what we have to do is we have to approximate the integral, which is known as a Riemann sum for everyone in calculus. But basically what it is we're constantly adding the current error times the change in time. So for every tick or every update, we'll be adding in a very small sliver of the area underneath the error versus time curve, because basically we're using rectangles to approximate the error versus time. I know this is that's kind of a confusing topic. If anyone has any questions, feel free to ask in the Slido question Q&A thing. So if that explanation really makes sense, I'm happy to rephrase it.
All right, so well, let's move on to the derivative portion. So I'll explain this part because it's really quite simple. So first we're just defining a variable, and then we'll call it derivative error. So I said we're just going to do the rise over run for this because we can't actually calculate the derivative because our error function is undefined. So we need to be able to approximate it. So we just do a rise over run to calculate the slope. So that's error minus last error, and that's error minus last over period. Right, that makes sense?
So it's because period is your current time minus your last time, and then that's error minus your last error. So this is the best approximation that we can do to the slope at that point.
Someone asked if we can explain the function we use for error sum is equal to 0. Okay, so this isn't actually checking if error sum is equal to 0 or not. What we did here is we're seeing if if in between the last time and then the current time, if our error function went from positive to negative or vice versa, or negative to positive. So math.signum will return -1 or +1 depending on the sign of the last error or error. So then we'll just checking if 1 is equal to 1 or yeah. So if the sign is different, we're going to reset the error sum, so it's the integral portion.
So the only time that the sign changes is when you cross 0. If you think logically, you can't change the sign without ever going through 0. So that means if we ever reach the target, then we should set the integral term to 0 to avoid the integral windup issue and avoid overshooting our target. Right now we're writing it in Java, but we're using Sublime Text just for ease of use. This, when you actually implement it, should be written in Android Studio, just as any other class like your teleops.
Yeah. So now we're gonna finish off their functions. So this would be the same as the equation that Sid showed, like the first one, and it's just also really simple. Double output is equal to.
Basically, we're just applying the constants to each portion of the error that we've already calculated previously. So this is the proportional portion, so kp times error, and then the integral portion, which is ki times the sum of the errors, and then the derivative portion, which is kd times the slope.
And for most of our use cases, I think we just didn't have any derivative at all because it's really not necessary for FTC.
And if you do have it, it should be a small amount. And then we'll just, the difference between Kp and Kd. So Kp is the constant that's applied to the proportional portion. So the proportional thing is just some ratio of the current error at that time. And Kd is the constant that's applied to the slope of the error versus time function. So meaning you should normally, KD should normally be negative because you should be subtracting the slope to smooth out the motion. KP should be positive, and because you're trying to actually reach your target. Does that make sense? If not, then just send another question. I could try and rephrase it.
All right, so last error will, so now we're just gonna update before we return the float. We're gonna update all of our, we're gonna update our time and our error. So that way our last error and our current error will be two separate things. So last error, so we're setting a last error to our current error, and then our last time to our time. And we do this at the end so that it doesn't mess up any of the calculations up here. But and next time update is run, it'll be using the last values, if that makes sense.
And then finally, we're just gonna return what our proper output value is.
Yeah, and then that's the end of that function. So that's, I believe that's our entire PID class. That's all the code that you'll need to have to make a PID controller work. Now I'm going to show an implementation of how to use this in
so we had a question on, is it possible for the integral value to be larger than the proportional value? I'm assuming you mean the constants for the integral and proportional. Normally we'll go over what like some possible constants are, but normally the proportional constant is far higher than the integral constant, because if you think about it this way, the proportional portion of your error will always be far smaller than the integral, because the integral is the entire area underneath the error versus time curve, whereas the proportional value is just the error at that time. Meaning you want to make your KP normally higher than your KI. And if you're saying tuning wise, if the integral portion should be more important, I guess, or more powerful in the tuning, I would say that's normally not a good idea, because the integral term is used to just fix your overshooting issue a bit. And what would happen is, if the integral portion was the main, I guess, driving portion of PID, your robot would move very slowly at the start because it's still building up, and then it would quickly jump up and exponentially increase its speed until it's crossed the target. And that would cause a great deal of overshooting and wouldn't be as accurate. And it would probably be slower too. But good question.
Yeah. So this is a teleop I just got directly from the FTC libraries.
This is just the basic tank drive.
Yeah, so
that's
you have
in the examples.
You have your left drive motor and you have a right drive motor. Really simple. So now I'm going to show how you can implement our PID controller class into this main.java. So all right. So first I want to just initialize some variables for the PID controller class. So that'd be, we're going to call that constructor we created earlier. So that'd be, actually, no, we're not going to call that yet. We're going to just define this as a null object, because, and then we're going to define it in a init, which we found to be a good idea generally. So because if we define it earlier, we can have problems with the robot like moving on an init depending on how your code is set up. And then now we also going to add our values KP, KI, and KD. So those are going to be final values because they're not going to be really adjusted during the course of your robot's movement at all.
And we're just throwing in some basic values. We'll explain why we chose these values.
Yeah,
actually,
so these are just our values that we actually used for our Y movement PID for our mechanical drivetrain for Skystone. So you see we have our large KP, smaller KI, and then an even smaller KD. And
actually, in our real usage, we didn't use KD, but we just wanted to show what an example value would be for KD.
Yeah, so again, really the best way to figure out what these values are, they're going to be different for everybody, depending on your odometry setup, your drivetrain setup, even different gear ratio motors, even sometimes your battery voltage. But the important factors here is that you need to have a lot of time to test your drivetrain with everything with a bunch of different values. So it's really just almost guessing and checking. But there are some ways that Sid showed earlier to try to steer yourself in the right direction. So in our init, now we're going to call that constructor we made earlier. So that's PIDY is equal to P. All right, and then we're gonna, so our first value would be our set point, then our constants. So we're gonna make this move forward 10. That could be inches or whatever units you want to use. And that'll depend on your odometry setup, which we'll kind of show later. All right, and then I think that's all we should have to add in init. And then, so now we're in our loop. So we talked about this update function being run every time we loop through our function, our auton. So we also created this get y position function. So this would be a function that would return a y distance traveled, and then you could figure that out by encoder or your odometers, depending on how you have your robot set up, essentially. But really, that's just getting your encoder output and then multiplying it by certain numbers to figure out how many revolutions you made.
Yeah, and normally you can find those numbers wherever you bought your motors or encoder or odometer encoders, and it'll show something like encoder value per revolution. So I think for ours it was 2048, and so if you just divide by 2048, you'll get your inches per revolution, or you'll be able to calculate how far you moved with some constant. And I'd recommend testing this a lot, because this is your main way to figure out your y or your position. And so if that value is off, it'll throw off your entire autonomous. So you want to make sure that part's accurate.
And that gets a lot easier once you get if you get odometry set up, which Pranay will talk about later. And that's because then we can just figure out the encoder value based on the number you find on the website, and then the circumference of the encoder wheel. All right, so now we're going to implement the PID controller class by using the update function. So we're going to rename this to correction, and this is what the value that we're returning right here. So that'll be equal to PID update. And this you see this calls for a new input. So our new input is going to be our get y position. So
right now, get y position is just kind of a dummy function. It's blank, but we'll let you guys figure out the best implementation for your situations.
And then since this is since we were moving in the y distance, we just forward and backwards, and it's a tank drive setup, we're going to have both of the motors be set to the same power. But one problem we saw was that this correction value would often be higher than 1 or negative, or lower than -1, which it doesn't really cause problems, but it's just recommended to set your your motor power in between a -1 and 1. So we can solve this by running this, and this will just clip your value in between -1 and 1. So take our correction, and we'll have the same code down here. And I think that's it. Am I missing anything?
Yeah, that's pretty much it for a basic implementation of PID, and the main and a basic application for PID. Yeah, so if you guys have any questions on the programming portion, please leave your questions in the Slido, and we'll be moving on now to the odometry. And then if any questions come up, we'll come back to the programming. So feel free to leave your questions.
One more thing. We'll be uploading our PID controller class that we made today and our main.java after the lecture. So you guys can look at that and use it as reference.
All right, I'll be screen sharing the presentation again. And all right, we'll be moving on to odometry, where Pranay will take over.
So the basic idea of odometry is you're using data from sensors to estimate your change in position over time. So I feel like the word odometry gets thrown around a lot, especially in FTC. So as Siddharth discussed, in their get Y position method that they created, you can get your Y position from the motor encoders and from using a dead wheel odometry system. So the basic idea of it is the same. So you're counting how many revolutions that your wheel does, and then multiplying it by the circumference of your wheel, and then that's how you can estimate your position. So so using the motor encoders to give you your feedback is still considered odometry. It's just in FTC, I think people use the word odometry more focusing towards dead wheel odometry. So so the problem with using motor encoders, especially when using mechanical wheels, is that, as you guys know, mechanical wheels have those slanted rollers on them, and then because of inertia, when your robot stops, it doesn't. When you set your power to 0, it doesn't actually stop because of inertia. The rollers keep spinning, and then that could throw off your. It will not. You won't be able to get to your target accurately. So this is where dead wheel odometry comes in. So the idea behind dead wheel odometry is that you're using a wheeled system independent of the motor encoder output readings, so that it's much more accurate because the slippage isn't taken into account. So in FTC, the most common implementations of dead wheel odometry is by using dead wheels for your X and Y, and using IMU for your rotation, or you can use 3 dead wheels and then use that extra dead wheel to measure rotation as well.
And we'll be sending out a video as well, like that someone else made on how to calculate your position with the odometer wheels and kind of the algorithms you'll need to use there. But we won't be going over that specifically in this presentation.
Oh, and we'll be sending all this stuff in the FTC online Discord. So if you're not in that yet, you should join that.
So the hardware for dead wheel odometry. So the basic stuff you will need is obviously the encoder, which you'll get your output readings from, an omni wheel, and you should use an omni wheel because say you're strafing, or so if you're strafing, then the wheel won't hold up the movement of your robot because of the rollers on the omni wheel, and then you need something to keep it all together. So as you can see in our picture, this was the dead wheel odometry module we used last season in Skystone. So the fundamental parts of it are pretty basic. You just have your encoder, which is that that black rev through bore we have right there, and then we have our omni wheel, and then there's a shaft going through the omni wheel and into the encoder. So since we use this this Andy Mark 2-inch omni wheel, so every rotation that the encoder picks up, we know that we have moved forward 2 inches. So if you're looking to buy the materials necessary for this, so we highly recommend using the rev through bore encoder, which was released last year, and this worked really well for us. And the wiring to Rev Hub is really simple. It was just like plug and play kind of. But there are a couple other options you could go with. So there's the CTR SRX Mag, which you can get on the Vex Pro website. So the advantage of this is that it's very small and very compact, so that if you're having if you're having a hard time fitting it into tight spaces, then it could be an option for you. And then as well, another popular one are the US Digital line of products, like the S4T, E4T, or E8T. But they pose their own set of challenges when it comes to wiring, because you need custom wiring in order to connect it to the Rev Hub. And also the encoders themselves are very fragile, so you have to be kind of careful with them. So just some basic tips and to look out for when you're implementing your own dead wheel odometry is that you want to eliminate as much play as you can in the system. So you don't want your dead wheel to be sliding back and forth on the shaft, or you don't want your whole module to be like loose on your robot, because that just introduces inaccuracies, and then it really defeats the purpose of having your dead wheel system. And then another good tip would be to make it as small as possible, because really you want to kind of put them on your robot and forget about it, and then have it so that you'll have enough room to implement the actual game mechanisms. And then also you want good wire management, because you don't want your encoder wire to come loose during a match, especially during your autonomous, because at that point it's game over and then everything's just down the chute.
Another thing that you could also implement is tightening, or making sure that your odometry module is sitting on the actual surface, and you can use this with rubber bands or whatever to hold it there.
Yeah.
And
so so like you'll have like inconsistencies in the floor mats or like certain obstacles and things. So you always want your wheels to be tracking. So in order to do this, we use suspension with rubber bands and force the wheels onto the ground, so that they, no matter if our robot like climbed onto something or hit another robot, then the wheels are always onto the ground and always tracking. So I actually designed this one a few weeks ago, and this was because I wanted to make it smaller for our next year's robot. So you can see here we have that aluminum shaft going through the Omni wheel and into the encoder, and it's important to use bearings, because you want this system to be have very little resistance, because you want to pick up all those small changes in position. And then if Sid can go back to the previous slide for a second. You can see on the front of our module, we have those bearings there. And this was because, as I discussed, we needed to spring load or rubber band load, I guess, the modules onto the ground. And then we needed to create like a pivot system, so that if it came into contact with an obstacle, then it won't just hit the obstacle, but instead it would kind of pivot and move up and respond to the environment, kind of. So we would have a standoff going through the module, and then that would allow it to pivot on that axis. And then, so it's important to also include those or a similar kind of system, so that you can have that pivot for your module. And then this is how a basic setup of how you would orient your odometry modules. So technically you could have them in any orientation, but then that's just extra work in order to calculate the different changes in position. So for the X tracking module, you would have it perpendicular to the robot's motion. So like, say you were strafing, so then the wheel would also be perpendicular to the robot's forward motion. So when you're strafing, then the Omni wheel would also be facing in the strafing direction, so then you can accurately track the strafing movement. And then your rotation and the Y odometers are oriented in the same, oriented to the forward motion of the robot. So like, if you say you want to move to like 10 inches forward, then you would use the output from those motors, from those encoders, to track your position. And then as as I discussed before, you don't have to use 3 odometry modules. Like we actually only use 2, and then we used the IMU on the Rev Hub, and then we did correction with PID.
All right, so that's the basic overview for odometry, and now I see that you guys have some questions, and we'll be addressing those. So the top one right now is, would the PID logic be the same for any type of like drivetrain, like tank drive versus mecanum? So the actual class, if actually I'm gonna stop screen sharing. If Niket, you could go back to the code, you'll see that the PID class is the same for any type of drivetrain, like no matter the type. the application of it is slightly different because if you have a tank drive, you'll only be moving forwards and backwards and rotating. So the actual implementation, like applying power and stuff, would be different, but the PID class would be no different depending on what type of drivetrain you have. So like for Mecanum, if you're trying to strafe, you'll be applying the power to the wheels in a different way than if you had an H drive, for example.
Yeah. So for example, if you're trying to use this PID class to do rotation, you might want to have set one of these to negative, and then because if one of them is negative and the other one's positive, then you'll be rotating. And of course, instead of get Y position, you need some sort of function to return how far you've rotated.
Yeah, and then another common implementation of using PID loops is for like lifts. So like say you wanted to place like a sky stone or something onto the foundation in last year's game, then you would have to use your lift or some other similar system if it's powered by a motor. And then to accurately make sure that your lift is also accurate, you could also implement a PID loop to make sure you're getting the proper extension and retraction that you need.
All right. And then the next question is, what would be some of the problems? If you could rephrase that question a bit. I think it was sent a while ago, so I don't exactly remember the context. But yeah, if you could send like a more specific question, that'd be great. We could address that. Someone asked, you have to use 2 Omni wheels. So you could either use 2 or 3, which Pranay can explain the difference with the
Well, I think I think the question refers to like a double stack of omnis, and if it does, then it's very important too, because if you just use one omni wheel that has one set of rollers, then the wheel is not perfectly circular, and this is problematic because say your wheel is oriented such that the roller is not perfectly in contact with the ground, then you're going to get inaccurate tracking, and then it could also introduce some resistance if the rollers aren't on the ground at all times. So that when you use a double stack of omnis, then the rollers are alternating, so that there's always going to be one roller in contact with the ground at all times. And generally, you'd want the wheel with as many rollers as you can get, because that will give you it'll get you to the most circular wheel as possible.
Another person asked, odometry uses data provided from sensors. By sensors, you mean encoders or something like a distance sensor? So odometry almost always uses encoders, so like the encoder we have on that picture, but you can use PID with other types of sensors. So for example, we used PID with just our motor encoders once, and we also considered using it with something like a ultrasonic sensor, measuring the distance from something.
Yeah, so PID is a very kind of abstract correction system. It can be used with literally anything that updates its value. So you could use it with a distance sensor, but I would like recommend using the odometry modules or motor encoders if you have to.
Yeah, and as Sid discussed in the very beginning of the presentation, PID can be used for literally any sensor, like in a coffee machine, for example. There would be something that would be measuring the temperature of the coffee, right? So then you would want to make sure that you're hitting that target temperature that you want for the proper temperature that you want your coffee.
Yeah, so then someone asked, could you highlight the differences between PID and dead wheel odometry? So PID is this error correction system, whereas dead wheel odometry is the odometry modules that's showing on the screen right now that actually track the position. So you use the output from the dead wheel odometry system to give an input into the PID loop.
Yeah, and then the advantage is using dead wheel odometry. So the dead wheel odometry is just the sensor setup. So you could use the motor encoders as well, and that would still you could use it. You can implement PID in that too.
Then next question is, what's the best type of wheel during the Skystone season? Pranay can address that.
So it really depends depends on your other mechanisms, like whether you had like a reverse 4-bar lift or some. It really depends on the rest of the design of your robot. So I know there's this very popular team called Data Force 6929, and they used a 6-wheel drive with the traction wheels. But and they were able to get away with this because they had a turret on their robot which their lift was attached to. So it wasn't really that important for them to orient themselves with the foundation very accurately, because they could just account for that using their turret. But then I think like a majority of the teams went with mecanums just because of the strafing capability, and that you don't have, if you're not perfectly in line with the foundation in order to place stones, or you're not perfectly in line to intake a stone, then you can easily just strafe or do some similar movement in order to accomplish whatever you're trying to do.
All right. Next question was, how much better is it to have 3 wheels for odometry? Niket could address that.
Yeah, so so you can do either 2 or 3 wheels, right? But what the third wheel traditionally does is it'll help you calculate rotation easily. Although we only had 2 wheels, so we were able to work around this by using the IMU to calculate our rotation, which was, I think, in my opinion, that was accurate enough for us. But if you wanted to have even more accurate rotation, you could have 3 wheels. Another use I've seen for 3 wheels is to have the third wheel act as a backup in case one of the other wheels fails.
Yeah, so rotation wasn't very important, or accurate rotation, I should say, wasn't very important in the season, in my opinion, because like in our autonomous, we only rotated once ever, and that was just to place the foundation. So that could be at any angle. So for us, having accurate rotation really wasn't that important. So we didn't prioritize 3 wheels, and the Rev Hub kind of suited us enough for that.
Yeah, another
Uh,
person asked if it's possible to use odometry or PID in teleop in a way that when the driver presses a button, the robot rotates 90 degrees. This actually is definitely possible. We even experimented with doing that ourselves, and it's definitely possible, and it would be pretty simple to do.
Yeah, so all you would do is I'd recommend just disabling the controller input while you do the motion, and then set your target for rotation once you set that up to 90, rotating, and then once you're close enough, then re-accept the controller input and then disable your correction update, if that made sense.
How does your robot deal with obstacles with dead wheels? So we were able to use our dead wheel odometry. So we had the 2-axis odometry where we had 2 wheels, and then because we combined that with our PID loop. So we actually experimented with literally just kicking our robot in the middle of its auto path, and what we'd see would happen is that because we have 2 concurrent PID loops running, actually we had 3. So 3, one for rotation, one for the horizontal movement, and one for the vertical movement. Not vertical, but like Y movement, I guess. So because of these 3 loops, we could, when it would see that it would deviate from its desired path, it would be able to correct itself by just the PID algorithm in itself was able to correct itself. So
Yeah,
that's pretty cool.
I think one of our slightly prouder moments was that we were able to do a park autonomous with only 3 wheels, and because we were able to correct for the XY rotation with our PID system.
Yeah, we actually put a screw into a gear, and then it stopped our back left wheel from turning, but it was still able to go straight because it just applied a lot of power to the left side versus the right side to fix the correction issues. Are there any other questions? If you have any questions, feel free to leave them. We still got a few minutes left where we could answer your questions. The biggest surprise that a robot gave. That would actually probably be it.
Yeah, when one of our wheels just stopped working, it was really confusing when we saw that it happen first, because we'd see because we just saw our Auton worked almost perfectly fine, but then our drivers were almost completely unable to control the robot, and we found out the only reason our Auton worked was because of our PID loops.
Yeah, so PID is very powerful if you can implement it. Any good books on odometry? I don't know of any good books, but there's a YouTube link that I can send here for now.
Yeah, and that video goes into more of like the theory behind odometry and then the algorithm itself.
Oh,
And
one
I
more
think,
thing.
yeah.
There's a Google form that you guys should fill out. It's to evaluate the presentation, basically. I'm pretty sure in the Zoom chat.
That's I just posted in the Slido for now. I'll post it in the Discord too, but this is just a video on like an introduction to the odometry system that we use with PID. Any online sources that goes into depth with PID. If I find some, I can send them again in the Discord. The workshop name is not on the Google form. I don't think we have access to the Google form, but the people who are managing this might be able to address that.
Yeah, maybe you guys. Yeah.
Do you mean like there's a different name on the Google form?
No. There's no name for our. There's
Just
a drop down.
general form.
There's a drop down.
Okay.
There's not a place for R. So that I assume will be addressed very soon.
Yeah.
Online sources that go into about similar thing goes into depth PID. Does that video you sent go into depth PID at all?
No, this is about odometry. But if I find some, I can send them. I actually think another team did something or is going to do something on PID.
That was odometry.
Okay, then if I find some, I'll send them.
We'll post all the resources we used for in the Discords. That'll be our slideshow and our code, and then you can
Yeah. Are there any other questions, or we could wrap this up? I'll give it a couple minutes. We'll probably stop at 4:30 if there's no other questions.
I just wanted to talk about our experience with using PID in our odometry system. Is that it just made everything so simple in terms of, instead of having to like, I know like teams try to do time-based auton, and then that usually takes a lot of time to really perfect. But then with using our PID and an odometry system, we would just input like, oh, we need to move forward 80 inches or like straight 40 inches. And then we could just put that in for our targets and then run it. And then based on the results we get from that, we just have to tune the PID values, and then that would be the end of it, really.
Yeah, I'd recommend having kind of a testing autonomous where you can just input random values to like make sure it does everything right. And yeah, all right. So
I think that's it.
Yeah.
Thank you
Any
guys
last
for
minute
having.
questions?
Is there any way like we could leave any way to contact us? Or actually, if you guys have any other questions, you can just add us in the first online Discord. I think we all have our team number in it, so anyone with 16236 in their name could direct it to the proper people to respond.
Yeah.
All right. Thanks for listening, guys. Thanks for your attention, and
yeah,
good luck in your next season.
Yeah, thank you guys.